may have it on your screen, you may not, but I'm also putting it on the big screen.
Yay. Another honor sign.
Okay.
Oh, well.
So today we're going to start talking about oxidation and reduction. Okay, oxidation reduction is basically another way of balancing equations in a lot of ways, but it historically comes from the term oxidation. What do you think the word oxidation refers to?
Like making rust.
Making rust is one thing, yes. What else? Oxygen may decay substances. Very good. Anybody else? Okay, those are both two examples of oxidation. And rust was the big thing that happened, that people started calling things oxidation because you were adding oxygen to something. You were putting it in, so oxidation, you were adding oxygen to it. So we called it oxidation. Okay, does anybody know why the Statue of Liberty is in the beginning of this chapter? Raise your hand. Raise your hand. Luke.
It used to be bronze, now it's green.
Yeah. What's that about? Who can tell me what that's about? It's actually, it is oxidation, but it's a special kind of. She wouldn't be there for over 100 years if that was like rust. Okay? Because what happens to rust?
Falls apart.
Falls apart, right? And so that is called a patina. Okay? A patina. That green, copper turns green in the elements. It is oxidation, and what that does, it forms, I'm going to talk a little bit more about it later on, it forms a protective cover. It only oxidizes the first layer of the copper. So the copper below the Statue of Liberty's outside is still copper color inside.
Like chisel it away.
Well, it's kind of electrostatically put there,
oh, okay.
So it's not going to go away. That's why it's so protective.
Would it eventually rust?
Well, you know, they did have some problems with the Statue of Liberty because it's right in the middle of the bay with salt water, so you've got lots of salt and stuff, and you have electricity going through very easily. So it did have some problems, but they're probably where joints were and things like that, where there was breaks in the patina. Okay, but usually that patina will go through and keep everything nice and structurally fine. All right. So this goes on. Why do you have to wash the bottom of your car sometimes? We don't have to worry about this that much in South Florida because we don't put salt on our roads because of ice. Okay? But if you live on the beach, I don't know if any of you live over on the beach, and if you live in or very close to the bay, your car may get a lot of salt on it from the bay or from the ocean. I lived right on the ocean when I first moved to Florida, and my car was constantly getting salt on it. Okay? So this will be a problem because the salt will dissolve with water, and that gives rise to corrosion or to rusting or oxidation. Okay, so we're going to look at a couple questions. What happens to substances that undergoes oxidation, and what happens to the substance that undergoes reduction? Now, reduction is a little bit different. Reduction was just the opposite of oxidation. So if something was rusting, wherever that came from, that substance was reduced. Okay, but we've got a more modern explanation we're going to talk about during this chapter for these two terms. Okay, so if you look at your automobile or any kind of burning, what do you need for something to burn? I heard it.
Wood.
Oxygen. Okay, so you need oxygen.
You need fire.
So you need oxygen. You always need oxygen. Okay? Okay, you need oxygen. Okay, and also in your body, the energy that you have comes from food, so your food is being oxidized too to make it ready for you to basically utilize those nutrients. Okay, so oxygen and redox. Okay, redox is kind of a word we created to mean reduction and oxidation. Okay, the type of reactions we're going to look at are called redox reactions, meaning if an oxidation occurs, a reduction must also occur. Okay, so this is basically what we're talking about when we're looking at these type of reactions. So if we have methane, for instance, and we light it up, it oxidizes. It actually forms carbon dioxide. So oxygen is actually reacting with it. This is one of the first ideas of what we were saying with oxidation. So we're getting new products. In this case, of course, since we have a combustion, our products are always carbon dioxide and water. We learned that a long time ago. Okay, but what we found out later on is that it didn't have to burn. You guys already mentioned what happens with rusting. Iron is something that rusts very easily, and it really rusts when there's water around. So what happens, what's the difference between rust and the Statue of Liberty, is that when it starts rusting, it makes it uneven. And so it makes it not stable anymore. It starts wearing away underneath because there's room for it to rust. It doesn't form a coating. It kind of just starts rusting something and some part is still exposed. That rust and so on and so forth. All right, things like bleach. Okay, bleach is, everyone heard of chlorine bleach, right? It's not Cl2, all right? It's sodium chloride, okay, hypochlorite. And it releases oxygen, and that's what does the cleaning for you. The same with peroxide. If you get a cut, sometimes you might put hydrogen peroxide on the cut. That means you're oxidizing it. Really what's happening is you're killing the bacteria because they don't like to see what happens. Both of those will kill bacteria because of what it does to them. As I said, reduction is the opposite of oxidation. Originally, reduction meant the loss of oxygen from a compound. So the loss of oxygen, because the oxygen was going to the other compound, it was oxidizing the other compound, forming rust or in the fire. So whatever it came from was being reduced. So that was what reduction meant, because we were looking just at the chemistry of the elements. So if we look at getting iron from iron oxide ore, which is the way it's formed, we would react it with carbon at a very, very high temperature, and we would release the iron and form CO2. So here we have, for instance, let me do it this way. Here we have the FeO3, which has the oxygen in it, and it's being released here. So it's the opposite kind of almost of the oxidation reaction. Okay, it also includes an oxidation process. The carbon, okay, oxidizes to carbon dioxide, okay, because carbon has no charge, but you could think of carbon dioxide as having a charge of +4 with the oxygen. So we're going to learn something. I'm going to tell you right now. This is where our transition occurs. So we're going to have something called, who knows the zodiac sign for Leos?
I'm a Leo. It's a
The lion. So, okay, so Leo, okay, the lion,
Why do you say it like that?
says, grr. Okay. Yeah, it's a different kind of grr. It's not GRR. Okay, Leo the lion says grr. Okay, Leo stands for loss of electrons, oxidation. Grr stands for gain of electrons, reduction. So instead of worrying about oxygen all the time, because sometimes it's not oxygen and hydrogen, it's other chemicals. And actually every reaction of ionic compounds, double replacement reaction, is actually an oxidation, redox reaction, because something's losing electrons, something's gaining electrons. And why is Leo the lion's anger? Because it always happens in pairs. If something's losing electrons, something else has to gain electrons. All right, this is an important fact. Substance that undergoes oxidation gains oxygen or loses electrons. A substance that undergoes reduction loses oxidation. That's an old-fashioned one. That's one way of telling you that. Okay, but you can't have oxidation without reduction. Okay, so we actually call oxidation reduction reactions redox reactions because chemists like to say things shorter than a big, long thing, oxidation and reduction. Okay. All right, and this is what we were saying. Today we look at it as a shift of electrons. So here's our new definition. Oxidation is now meant that something that either completely or partially loses all of their electrons or gains oxygen. Okay? Reduction is now defined to mean complete or partial gain of electrons. So as I said, oxidation, Leo, reduction, Ger. Okay? If you remember that little mnemonic device, you'll always get it right. Okay. When you have a reaction between a metal and non-metal, electrons are transferred from atoms for one thing. So here we have magnesium and sulfur. Magnesium, if I heat it up with sulfur, I'll form magnesium sulfide. All right? So any element has an oxidation number of 0. But magnesium sulfide, magnesium has a oxidation number of, where is mine? Let me see if there it is. So magnesium here has these two things have an oxidation number of 0, but magnesium is going to be +2, and sulfur is going to be -2. So what happened to magnesium's electrons? What happened to the electrons in magnesium? Can anybody tell me?
Given away.
They were given away because it has a positive charge, which means it has 2 more protons than magnesium. So magnesium went through oxidation. Okay, what happens to sulfur? Sulfur has a -2. It has 2 more electrons. So it gained 2, so that's the reduction. So magnesium was oxidized from 0 to +2, and sulfur was reduced from 0 to -2. So by increasing the more, if an oxidation number goes to a more positive number, it's oxidation. If it goes to a more negative number, it's reduction. So for instance, if you were 10 plus 4, okay, if we had 10 plus 4, let me see if I can write that somewhere. And I went to 10 plus 2. What kind of reaction would that be?
Both.
Yes, because it's gaining electrons. It's becoming more negative. Even though, okay, so it basically gained electrons, okay, because it gained 2 more. So even though both of those are plus, you're going in the direction of more negative. All right, so once in a while they'll throw you a curve like that. Okay, usually it's very simple. You're going to see one get positive, one get negative. But sometimes you'll see something like 10 plus 4 going to 10 plus 2. So be careful. Make sure you're thinking of getting more negative or more positive when you look at it. Okay, so basically this is just the same thing I just went over. They're just showing you the electrons this time. And they're showing you where the magnesium has donated its electrons to the sulfur. Okay, and sulfur is accepted to it, and when they do it, you see a change in charge. So magnesium is giving up its electrons, so we call that a reducing agent. Something that's oxidized is a reducing agent, and something that is reduced is an oxidizing agent. It's oxidizing the magnesium. It's stealing their electrons. Okay, and that's basically what we just said. All right, so when we write a redox equation, we can separate the two things into two parts. The magnesium part, instead of writing, for instance, the whole equation, we say magnesium metal goes to magnesium 2 plus 2 electrons, meaning the electrons came away from the magnesium. The sulfur gains these 2 electrons to become sulfur 2 minus. So these are called half equations. Okay? These half equations are basically so we can separate the oxidation part and the reduction part. Okay? So you'll see that a lot. All right, so what? So again, Leo the Lion says Gur. Yes. And as I said, the substance that loses electrons are called reducing agents. The substance that accepts electrons are oxidizing agents. All right. I think that's pretty self-explanatory, that slide. All right, let's do a real case scenario. Silver nitrate reacts with copper to form copper nitrate and silver. From the equation below, determine what is oxidized and what is reduced. Identify the oxidizing agent and the reducing agent. Okay, so silver nitrate. So what happens to the silver? It goes from silver nitrate to silver. Elizar, can you tell me what happens? Because I know you're paying attention 100%. Right? When I do this, I expect you guys to not be doing anything else but listening and taking notes. Okay, so silver, what's the oxidation number of silver and silver nitrate? What's nitrate? You guys should all know nitrate. You've used that a lot.
-2.
Nitrate's -2?
-3.
No,
4.
-1.
-1. So silver is +1. And what's silver over here as a element? What's silver's charge when it's an element?
2.
Silver.
Does any element have a charge?
Yes.
No, not when it's by itself. So its charge is 0.
50-50.
Okay? So if you're going from +1 to 0, is that oxidation or reduction? Reduction. You're getting more negative. So this part here, the silver to the, I'm really drawing that very poorly. The silver to the silver metal is reduction, RED. Okay, our other metal is copper. Copper is by itself, so what's its charge if it's by itself?
0.
0. It's always 0 if it's the element.
Is this only for this? Like, is the 0 only for this?
If the element is by itself with no charge on it, it doesn't say aqueous or something like that, every element has no charge if it's the elemental form of that metal. Okay? So for instance, metals would be 0. Cl2, chlorine, 0. Okay? So this is going from copper 0, but it's in copper nitrate, but there's 2 of them. You just told me nitrate's -1. So what's the oxidation number of this copper here? What's this copper's charge? There's 2 nitrates. So copper must be what? +2.
Cancel each other out to make 0.
So it's going from 0 to +2. What's happening there?
Reduction. Or oxidation.
Decide. It's one of those two things.
Oxidation.
You sure about that?
Yes.
Why?
I don't know.
Who can help them out? Why?
They lose. They lose electrons.
They lose electrons. It got more positive So this must be oxidation. And you kind of got a little reprieve there because you saw reduction was already there. So it had to be oxidation. All right? So if you've already said something's reduction, the other one has to be oxidation. Okay, so you look at it that way. So there's always something that's oxidation. There's always something reduction in these type of things. Okay, so we just identified the ions, and we kind of went through the whole process that they're going to go through. Okay, so they rewrote the equation for us. Okay, so they went through everything I just asked you. So Ag is plus, copper is 2 plus on the right-hand side. This copper has got no charge on the left-hand side. Ag has no charge on the right-hand side. So they're basically showing us what's happening, that copper becomes copper 2 plus, and Ag plus will become neutral Ag. Okay, so that's a nicer way of writing it, because I don't write that neat. We know the species that loses electrons is oxidized and is the reducing agent. So therefore, copper, you told me, is oxidation. So this is how we write its half equation. And silver goes under reduction. So that's how we write that equation. Okay, so what about covalent compounds? They were everything we looked at so far were ionic compounds. We can do exactly the same thing, okay? Because technically, we treat them like they were ionic compounds, okay? So we know H2 and O2 are by themselves, so they have zero charge. However, if oxygen was in an ionic compound, what would its charge be? What would oxygen's charge be? 2 minus, okay? So that means, and what would hydrogen be? Plus 1. So we can actually say that we are using what's called oxidation numbers instead of charges. I've used that term interchangeably, but oxidation number is really specifically designed for covalent compounds. It means it's not a real charge. Rebecca, would you like to teach right now? Because obviously you must know this. All right. In each reactant hydrogen molecule, the bonding electrons are shaped equally between the hydrogen atoms. Well, that makes it covalent. Same with oxygen. But in water, we know water is polar, okay? Because we have a little bit loss of electrons. All right, so we can see that in the picture. So since we're actually moving some of these electrons towards the electron cloud, the oxygen is kind of being reduced. And this is kind of giving you the theory behind what we're going to talk about. So since we have those polar molecules, it's basically shifting the electrons towards the oxygen because it's more electronegative. So oxygen is the one that's going to gain electrons, and hydrogen is going to lose the electrons. Okay, so hydrogen is being oxidized. This kind of goes back to the original definition, and oxygen is the oxidizing agent. Okay, but we can also just simply treat it like a ionic equation and get the same idea. Okay. So what happens in covalent compounds? The shifts are a lot less obvious, okay? Because we know in ionic compounds there's a complete transfer of electrons. Okay? So in covalent compounds, there's basically that polar shift, or there's a gain of oxygen, or loss of oxygen. So these are the things you can look at for covalent compounds to see what's happening. All right? So you might want to take a screenshot of that if it's on your sheet. All right, let's ask a question. The element that donates electrons in a redox reaction is called the reducing agent. Which of the following is always true of the reducing agent? Don't shout it out. Think about it for a second.
B. F.
Thank you for shouting something out. I said don't shout anything out. Okay, who would like to raise their hand?
B.
B, it is reduce. How many people agree with Ronald that it's reduced? The reducing agent is reduced.
Yeah. No, I'm just kidding. I was kidding. I pick A.
I pick C.
I picked C too.
No, I pick C.
I pick C.
No, I'm still with A.
A reducing agent is always oxidized. An oxidizing agent is always reduced. If you see agent, whatever it says in front of it, the opposite thing is happening to it. Okay, because it's reducing something else. That means it's providing electrons to something else, so it's losing its electrons. All right.
So got it right, basically.
You didn't get it right, and he didn't get it right at first until I questioned his answer.
So it was A. Man.
All right. Okay, corrosion. What is corrosion? Corrosion is what you typically call salt. You call rust. It's just saying that, like in the Statue of Liberty's case, because there's all that salt water around it, it's going to make it a lot easier to corrode or rust. Okay, it basically enhances the rate of corrosion. And corrosion is a fancy name for rust. All right, so here's an equation that shows why water makes this happen more easily. What you form is the hydroxide of the metal first, which is very, very strong at dissociation. Okay, and then there's more oxygen, so you keep on making more of this iron hydroxides with different oxidation numbers. Okay, so it accelerates it because you have these intermediate compounds that are results of the oxidation. So instead of forming iron oxide, you're forming these hydroxides. So all you really need to know about that is if you have salts or acids or water, the rate of rusting will increase. You don't have to...
Go get him.
Are you okay?
Get that money.
No, dude, not voiceover. Stop. That's
What happened?
Who did this?
FLPX folder. You are currently on a folder.
Turn it off.
Muting.
And I didn't do anymore. It's because that's all.
Why would you tell him?
All right. So if your car is exposed to salt,
Call 1-800-444.
why is it important to wash off your car? Because corrosion will happen much more quickly. All right. Now, you guys, we talked about this with the Statue of Liberty. See how this building that has the green metal on it, that was originally brown, copper, when the building was made. All right? But it forms this patina, which is basically a film of copper to carbonate, which protects that copper from further corrosion. It's nicer. People do it on purpose because have you ever seen a building that's just been made and it's got a copper roof?
Yes.
And after about 5 years, you start seeing it turn green. Okay, now gold and platinum are called noble metals. Okay, and it has to do with their electron configuration. If you look at the number of electrons they have a full set of d electrons. Okay, they have 10 d electrons in their outer shell, or second last shell. And that's a very stable configuration. It's kind of like a mini noble gas configuration. That's why gold and platinum do not make many compounds. Okay, because they're very unreactive. Okay, so that's why in your electronics, a lot of times they'll use gold, which is expensive, but it keeps those electronics from corroding and going bad. So a lot of things in your computers will have gold plating on them so they don't go bad. Okay, then some things, of course, like we just mentioned, they can lose electrons easily, but they have a coating or a patina that keeps them from corroding further. Okay, and here's the picture I was talking about earlier. On the left, you have iron, and you see those kind of like where the surface doesn't all change. There's like little breaks in it, so it can keep on eating through surfaces lower and lower in the iron. Whereas aluminum, if you look at the aluminum forms a patina also, and you can see that it protects. There's no channels that can corrode further in it.
And that's what phones are made of. iPhones are made out of aluminum.
Yeah. So, well, okay. Does anybody know aluminum? What's on top of the Washington Monument? Of course, you're going to get this very easily. On top of the Washington Monument, it's not cement. It's a piece of metal. What metal?
Oh, Abraham Lincoln.
Oh my God.
Aluminum. Okay.
Oh,
That was this little triangle of aluminum is at the very top. Okay? Pyramid of aluminum, yes. And so that was very, very expensive.
so I
Well, wait a second. That was very expensive, but you can go to the store and buy aluminum foil for like $3. Why was this pyramid of aluminum this little teeny pyramid of aluminum so expensive?
Because it doesn't
Pure.
rust. It doesn't rust. It has gold in it.
It
The
does
aluminum
rust.
foil is very pure too.
It has gold in it.
Nope.
Nope.
Aluminum was almost as sought after as gold when the
So it's like harder back then to find it.
it wasn't so hard to mine. It was hard to process from the ore. All right, so they could get the rocks, just like the rocks that gold is in, but to get the aluminum out of it took a lot of energy and a lot of money to clean it up. So to get pure aluminum was something really special. Okay, but then somebody called Bessemer came along, and he found a way of doing it that was fast and cheap. And so that's why we have aluminum today that we can cover up our bowls and things like that with, or we can build airplanes with it because it's not as expensive as it used to be. Okay? But that's why it's at the top of the Washington Monument, because it was thought of like putting gold up there. All right? All right, what's some other things we do to keep things from rusting? We paint them. Cars are painted for this reason. That's why you have pretty colors on your cars. Not because it's pretty colors. It's because it keeps the metal from rusting as easily. It's still plastic. A lot of times, sometimes they dip things in a plastic. And what they basically do is they keep the air and water from touching the metals. Okay, someplace where you might see this is on bridges. In San Francisco at the Golden Gate Bridge, they paint that bridge kind of a reddish orange color. That's a full year job. Okay, once they finish painting it, they start on the other side again, because it takes that long to paint the whole bridge.
I've been there.
Yeah, me too. And so they basically start.
Oh my God.
They start and they keep up, and they go back and paint over it. So
I wouldn't be able to do that.
I couldn't do that. I couldn't do that.
I would fall big time.
I'm not that scared of heights, but
No, but
That's
they're
like that.
They're like attached to it, right?
I know. I had some friends a couple weeks ago go to Australia, and there's the bridge in Sydney that you can climb up on,
Oh yeah.
and they climbed up on it and walked up to the top of the bridge.
I'll be the first to fall.
All right. The other thing that might be on your car is chrome. Okay, chrome is also chromium is a metal that makes a protective coating, and so it forms a patina also. Oh, this is another way of keeping something from corroding. Is you have a metal that's more easily oxidized. Okay, so you might coat it with that metal, or you might put a little piece of the metal on it, so that instead of iron corroding, the magnesium will corrode. So we sacrifice that metal. Zinc. Most sinks are coated with zinc, because zinc will oxidize before the iron oxidizes. So a lot of times you hear the word galvanized nails, galvanized garbage cans. Okay, garbage cans, if they get run over by the truck, sometimes they'll start rusting because they've broken that surface. All right, but they last a long time because they have this coating of zinc on them. So here we have a piece of zinc, and I think it's on a ship, okay? Because the ship is near the sea with lots of water and salt, so therefore this zinc keeps it from rusting, because if it rusted, then all of a sudden it's easy to get a hole, and then it's easy for the ship to sink. And I just explained this to you. All right, here's some key concepts. I'm going to read them for you. You can read those. Okay, there's your definitions of oxidation and reduction. Just remember Leo the line says Gur. Remember that, you're set. And what Leo the line and the Gur means. Reducing agents, it reduces something else and itself is oxidized. Oxidizing agent, it oxidizes something else and itself is reduced. Okay, the big ideas for this section is oxidation reduction reactions always occur simultaneously. Very important. Leo, Gur. If oxidation is involved in the reaction, then the substance gaining oxygen is oxidized, while the substance losing oxygen is reduced. The species that is reduced is the oxidizing agent, while the oxidizing species is the reducing agent. That's the nutshell of this section. All right, so that's it for section 1.
Where do we say when it's very entertaining?
You're still being recorded.
Can I use the restroom?
You may.
Oh, can I go out?
Sir, can you ask a question?
Yes.
That background